All right, folks, we're going to talk about conservation of momentum. Conservation is one of the big underlying themes of most sciences. Things that are conserved. We've already talked about a few things being conserved. What was the other thing we talked about being conserved?
Energy.
Energy, right. Energy is conserved in all systems. Well, God, just like energy is conserved, so is momentum. Momentum is conserved even in collisions. So I want to show you a quick little video.
This may just seem like some gratuitous violence, but there's actually some really interesting science going on when you compare these two impacts. You would think that doubling the speed would give you twice the severity of the impact, but the physics says you're actually looking at more like 4 times the severity of the impact. Our sensors are showing 3 times the G's, and our wreckage is showing about twice the damage. So what's going on here? Well, just like this can, the more I crush it, the more it resists crushing. There's some complex physics going on here, but you don't have to be a rocket scientist to understand it. The cars speak for themselves.
They certainly did. And after 2 spectacular crashes, they have their benchmarks for car carnage.
Well, we've got our data points.
And they are lovely. I guess it's time to move on to the main event.
Yep.
This car right here hit a wall at 50 miles an hour. This car hit a wall at 100 miles an hour. I think the difference is pretty clear.
Same
The
car.
question is, when we smack 2 cars together at 50 miles an hour, are they going to look like that? Or are they going to look like this? We're going to smash 2 more cars just to find out.
It's the final act of Carmageddon. 2 cars in a 50-mile-per-hour head-on collision.
Here's how this breaks down. At this end of the track, the yellow car.
And at this end sits the orange car.
And here in the middle, these 2 cars will meet in a 50-mile-per-hour handshake of destruction that will hopefully answer all the questions we have about the crash forces involved.
Adam's predicting those answers will give the thumbs up to Newton.
This one has really been a brain bender, but I have a prediction for this final experiment. I think that when all is said and done, it's going to prove that Jamie was wrong and that the fans were actually right. That when these 2 cars hit 50, they're going to look like the car that hit the wall at 50, not the one that hit the wall at 100.
And Jamie agrees.
Based on our small-scale testing, what we should see at the end of this head-on collision should look pretty much like the 50-mile-an-hour crash against a wall.
It's crunch time for force impact. Will the full-scale test prove the fans right?
That's it. Well, I think it's time to do the final test. They're all set up.
It would seem so. I'm going to call it. Bring on the head-on collision.
From each end of the 1,280-foot track, the identical 1.5-ton cars take off. Both cars gain speed as they head headlong down the track towards their head-on collision. Then, as both cars reach 50 miles per hour,
It's about to happen.
the cables uncover.
What can you say?
What can you say? That breathtaking finale is the final piece of their physics puzzle. And as the Mythbusters survey the wreck of a 2-car 50-mile-per-hour pileup, they're playing Spot the Difference.
There's a windshield between them.
It's pretty evident, isn't it?
It really is.
It looks just like the 50-mile-an-hour against a wall crash.
And nothing like 100.
Nope.
Amazing. This tells me the whole story. I don't need to see the accelerometer data or anything. These 2 cars, which hit each other at 50 miles an hour, look exactly like a car we smacked into the wall at 50 miles an hour. That tells me everything I need to know.
So if you look, essentially what's happened there is energy, the momentum Essentially what's happened there is the momentum of each car got transferred to each other, okay? So that's kind of what's happening. We're talking about, if both those cars were the same mass and they're both moving at 50, what's the total momentum in the system to start? To start, what's the total momentum in the system? Zero. Why would it be zero? Right, because one would be positive and one would be negative, right? One would have a positive velocity and one would have a negative velocity. Remember, it is important what you call positive or negative. So the law of conservation of momentum says that the total amount of momentum of all the interacting objects remains constant regardless of the nature of the forces between the objects, okay? So really what they're saying is this formula. They're saying that the total amount of momentum in a system is before and after a collision or some interacting of the objects should be equal. I write P total initial equals P total final. Now, if there were two interacting objects, what would it turn into? Two interacting objects like the cars. It would be P1 initial plus P2 initial equals P1 final, P2 final. So you could turn it into that. And then, of course, we've also got, we could substitute in our formula for each of the momentums, which would be M and V, M and V, M and V, M and V. Now, here's where it's really important. It's really important that you use subscripts. Why? Because you're going to have interacting objects. I need to know, there's going to be two different masses, right? And there's going to be four different velocities. So we need to know which of the masses is it? So that's why you got to have that subscript. And is that the velocity of object 1 or object 2? And is it before or after the collision? So you have to, it's really important that you use subscripts and that you're very clear on this, okay? Ironically enough, this is actually a reflection of Newton's third law. Remind me what that was?
Object that...
No.
Third law said?
Mm-hmm. Boy, I learned you guys something, didn't I? Get it, Del Sharia. For every action, there's an equal and opposite reaction, okay? So let's talk quickly about what this really means, what this would be in certain situations. Let's say I was riding on a skateboard, right? And there was another student riding on a skateboard ahead of me. I was riding faster than him. Notice my vector is longer than his, right? Then that would indicate that I'm moving faster. We would collide at some point because I'm moving faster than him. And then he would end up moving faster after the collision. I would end up moving slower. Well, in that situation, P total initial equals P total final. We've got the P of both of us to start. And then we've got the P of both of us to end. So it would be MV plus MV, MV plus MV. Now, let's talk about a few other situations that might be slightly different. For example, let's say I was standing on a skateboard, okay? And as I'm standing on a skateboard, Daykel, will you grab me a skateboard? Please, thank you. And as I'm standing on the skateboard, we're not moving, right? In this situation, we are moving, okay? We're moving along this way. And then I jump off of the skateboard, and what's going to happen is the skateboard is actually going to go backwards. So what's going to happen is I'm going this way, and then I jump off, and the skateboard goes this way. Yes, absolutely, right. So in this situation, and this is the only situation that might get a little tricky. In this situation, we are acting as one object to start, you see? So we would have to add the mass of the skateboard and me together, and we would have one combined velocity. After I jump off, we're two separate objects. So we would have MV plus MV. So be prepared if two objects either are acting as one to start or they collide and become one at the end, then in each of those situations, you would need to do M plus M times their combined V. Okay? Let me give you another situation. In this situation, we've got the skateboard coming at me. So I've got the skateboard coming at me. I'm going toward the skateboard, and then we jump on and we move together, okay, afterwards. In that situation, before we would be separate objects, so it would be MV plus MV. And then after we became one object, in that situation, it would be M plus M times V. This is what we call an inelastic collision, and we'll expand upon that next class, okay? And then last but not least, this is the lab we're going to do next class, okay? What if, this is kind of what they call an explosion, and what if I was laying on a skateboard and I had a bowling ball in front of me and I pushed the bowling ball really hard one way, then but to start, we would have no momentum. You with me? We had no motion, right? Because we had both of our velocities was 0. After I push it, we each have momentum. The bowling ball has momentum that way, and I have momentum going backward this way, right? So that would be mv plus mv. But one thing that's really important, and this is something that you need to be very careful of, momentum is a vector quantity, so direction matters. So in that situation, if I call the bowling ball's velocity positive, what do I have to call my velocity? Negative, okay? So this is what we call an explosion, when there is no momentum, and then all of a sudden there is momentum, okay? And this would be a good example of sort of like, you know, in an explosion, there's no momentum of any of the objects, and after it explodes, all the objects are going different directions. But guess what? If you added together the momentums of all those little objects, guess what you'd end up with? 0. Because momentum is conserved, okay? Let's go back here and see if any of these videos might be helpful to you. No, that's not, we won't watch that one. And then
rose for over 200 years. Collisions were an active top.
that's a good end point right there, okay? We'll talk more about conservation of momentum and do the we-dos next class. Good job today.